ওয়েলকাম ব্যাক। এর আগে ভিডিওটাতে কিছু একটা টেকনিক্যাল প্রবলেমের জন্য থেমে গেছিল। সো উই আর রিজিউমিং from where we stopped. We are discussing about the principle of D'Alembert's principle actually, and we have seen that the forces, external force with the reverse effective force is in equilibrium, right? Now, if that is the case, then we can apply the principle of virtual work. So, for principle of D'Alembert's, you are considering D'Alembert's principle. Sure. D'Alembert's principle, right? So we have seen that summation over I Fi minus Pi dot, right, delta Ri, this will be equals to 0, right? Because Fi along with the reverse effective force Pi is in equilibrium. Now the applied force can have, as usual, force of constraint or external force. Summation, oh sorry, I'm sorry, one summation is there. So Fi, one part is say external, I am denoting is external, plus force of constant Fi, right, minus Pi dot, right, delta Ri equals to 0. So this leads to summation over I Fi external dot minus Pi dot of delta Ri, this is equals to 0, since Fi into delta Ri, this equals to 0 dot of delta Ri, because force of constraint do not involve work, force of constraint do not do any work. আমি একটা এক্সাম্পল দিয়ে দেখিয়েও দিয়েছি, যেমন ফোর্স অফ, যদি সিম্পল পেন্ডুলাম ক্ষেত্রে 10 সেন্ট হচ্ছে ফোর্স অফ কনস্ট্রেন্ট, তো যেহেতু ডিসপ্লেসমেন্টে তার পারপেন্ডিকুলার হচ্ছে, তাহলে তার ওয়ার্ক ডান হবে না। তাহলে দিস ইজ দ্য প্রিন্সিপাল অফ D'Alembert's principle. Now we'll see that this is the only, this from this principle Lagrange's equation can be derived. We will derive Lagrange's famous Lagrange's equation from this principle. But before that, we have to consider generalized velocities and generalized displacement, right? Generalized displacement and generalized velocities has to be considered. After that, we can move to the formation of Lagrange's equation. But the application of D'Alembert's principle, in application of D'Alembert's principle, I have taken two examples for the application of D'Alembert's. This is this applications are important in terms of the examination, because in examinations questions will be there for applications, but for the discussion or discussion of the Lagrangian formulation, this is not so important, but it is important for the examination point of view. So I'm taking the example of D'Alembert's principle, application of, I'm sorry, so I'm considering application of D'Alembert's principle. I'll give you three examples, three problems I'll give you. First one, I'll work it out so that you can, most of the part I will work out First is say simple pendulum. Simple pendulum. Suppose this angle is theta, right? Then how you can apply D'Alembert's principle to find the equation motion of a simple pendulum. By the way, I have given you a task to find the equation of motion for a simple pendulum using Newtonian mechanics. I don't know whether you have done it or not, but I have not checked it yet. It is very essential to do it for your own, that use Newton's second law of only Newton's second law. That means there a single particle is involved, so you know the forces. This force is T, this is mg downwards acting. So considering these two forces, you find the equation of motion. But here you apply D'Alembert's principle. Suppose since T is force of constant, right? So say suppose there is a displacement delta Ri, right, perpendicular to T, right? Now if the length is L, then we can say that mm, P equals to momentum. P will be equals to m into v, right? Now what will be the v? You know, it will be ml theta dot into theta cap. What is the direction of theta cap? Theta cap is the direction in the direction of delta Ri, right? Because this is generalized some polar coordinate r theta. Since r is constant, r is equals to L, so we made it. You know this is the L theta dot r theta dot theta cap plus r dot. This is the expression for velocity. You know, velocity in polar coordinate, r dot r cap plus r theta dot theta cap, right? That was the expression. But now in this case, this will be 0 because r is constant. This is equals to L. So this will be r theta dot, where r equals to replaced by L. So L theta dot, and its direction will be theta cap. So now you can write that delta Ri displacement will be equals to delta r into theta cap, right? Now we apply principle of virtual work, right? So you have to calculate P dot. P dot will be equals to m L theta double dot theta cap plus m L theta dot del theta cap by del theta into theta dot, right? You have learned it in your previous classes. So it will be ml theta double dot theta cap minus ml theta dot square r cap, where r cap is the perpendicular to theta cap, right? R cap is perpendicular to theta cap, right? R cap is perpendicular to theta, and del theta cap by del theta will be equals to minus r cap. You have learned it in your first year mechanics classes, when you are considering the polar coordinates, right? Now we apply D'Alembert's principle. Applying D'Alembert's principle now, applying D'Alembert's principle, D'Alembert's principle. principle, D'Alembert's principle, we see that so one particle is involved, so we are not uh, giving the summation. Actually, principle was that if I external minus pi dot delta, right? This was the principle. Now, since one particle is involved here, so we are so if I external is the force mg and its direction, I am writing this as j cap. Okay, negative sign, right? Because I'm taking y direction up to be upwards. So the mg j cap plus another force is there. You can consider it because this is force of constant and I am consider external force. So t has you don't have to consider t. So then minus p will be equals to ml theta double dot theta cap plus ml theta dot square r cap dot of delta r into theta cap. That will be equals to 0. Now taking dot product j dot of theta cap, right? J is in this direction, j is in this direction, and this angle, this angle will be 90 degree minus theta, right? So j, this will be minus mg sin theta. So this will be minus mg sin theta, 90 degree minus theta mg sin theta, and this will be ml theta double dot, and this r cap and theta cap since perpendicular, so this will be also 0. So I'm sorry, this will dot of I'm sorry, this dot of delta r will be equals to 0. Now this is important. Now you may cancel out the m may cancel out, so theta double dot plus g by l sin theta equals to 0. That means theta double dot plus omega square theta equals to 0. So this is the, I'm writing it just below, writing it here, theta double dot plus omega square theta equals to 0. This is the equation where omega equals to root over g by l and sin theta equals to theta for small angle acceleration, angle consideration, right? Approximation. So you find the equation of motion by applying D'Alembert's principle. This is very simple. Only thing that you have to consider is the virtual displacement delta Ri. Why it is virtual? Because the particle will eventually move in this path. So this delta Ri is a virtual displacement, and since forces mg and t and the reverse effective forces are in equilibrium, we apply principle of virtual. And the second example that I can give is very simple. First example I have done it. I'm sorry. Example 2. I hope you can do it very well. Suppose a box is rolling down. It has a mass m, and this wedge has a mass m. Right? This mg is acting this way. So this angle is theta. So find the acceleration of the box m sliding down an inclined plane, applying D'Alembert's principle. I think you can do it on your own, right? What you will do? The force acting is mg, right? F equals to mgj, right, minus mgj, right, and p equals to mv will be equal to mx dot, where you consider this direction to be x. Then delta r will be equals to delta x into x cap. Say this is the direction of x cap is the unit vector along this direction. Now apply D'Alembert's principle. There will also be a force, right? Force reverse force. That means reaction force R will be there, but you don't have to consider that thing because the displacement is perpendicular to that. So we apply D'Alembert's principle and find the acceleration. You know the answer. What will be the answer? But I am giving it a little bit twist. Now you see the this uh, case one. In case one, m is much larger than m, and case two, m is also moving. Then you can apply D'Alembert's principle. How we can apply it? Then there are two particles, right? So for particle 1, say delta x is the displacement. For particle 2, I consider, so the same problem, x, I consider this y, right? Then considering uh, the motion, and there is a relation, there will be a relation. The relation will be what? The relation will be m into the mass is m, mx will be equals to say, or m dx will be equals to m plus m. So this is capital M y, but the whole component of this thing will not be there. Then m dx cos theta. Sorry, it will be m cos theta dx, right? Since dx is in this direction, this angle is theta. If this angle is theta, then this angle will be theta. So when it is moving, then in x direction, it is moving in the negative x direction. So this displacement and this displacement has to be in equilibrium, because there is no force along for this. It has to consider for center of mass of the system, right? Cm to be static along x. I'm sorry, along horizontal direction, right? Along horizontal direction, right? Now you have to apply D'Alembert's principle. So here two particle is there for one particle. So summation over Fi minus Pi dot, right, delta Ri. Now for particle 1, Fi is mgj, right, minus Pi dot is how much? Pi dot is mx double dot x cap, right? Now for the second particle, there is no external force, right? So it is equals to 0, minus the Pi dot will be equals to m plus m y double dot, right? Right, and the corresponding displacement, displacement will be, this will be, say, delta y. This is this displacement is delta y, right? So this will be delta y, the vector side. delta y, and this displacement will be this displacement dot of delta x, right? So this will be equals to 0. So now j dot of delta x, j is acting in this direction. I am considering minus j, so j is actually in this direction, and delta x is in this direction. The angle is 90 degree minus theta, right? Sorry, 90 degree plus theta. So there will be a minus sign, so this minus will cancel out. It will be mg sine theta, right? This will be mg sine theta, and this will be minus mx double dot delta x minus m plus m y dot. Now from this relation you can find that y dot will be equals to m cos theta by m plus m x dot, y double dot will be equals to m cos theta by m plus m x double dot, right? And also delta y will be equals to, sorry, this will be delta y, this will be delta x, so, right? So delta y by delta x, so delta y will be equals to m cos theta by, so there m is so m plus m y dot will be equals to m cos theta x double dot, and for delta y it will be, for delta y it will be m cos theta by m plus 1, so the altogether it comes out to m square cos square theta by m plus m into delta x equals to 0, right? Now you find one m will go this m and one m will go, so x dot will be equals to g sine theta by 1 plus m cos square theta by m plus n. So this I have done, right? Now your own homework is find it is very easy, y double, find y double. So application of D'Alembert's principle for these three examples I have shown. Next, I just consider very quickly generalized displacement and generalized force, right? Very quickly, that what is generalized displacement and generalized force. Number one is generalized displacement generalized displacement. Suppose we have I'm sorry, generalized coordinate qi, right? That means q1 q2, that means q1 q2 dot 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 qn, n number of generalized coordinates are there. So this will be function of position coordinate ri, this will be function of generalized coordinate q1 q2 dot 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 qn, right? Then displacement delta ri, then generalized displacement is delta ri will be equals to del ri by del qi delta qi summation over I, right? Plus del Ri, this is also be function of time. If the transformation del Ri by del T into delta T, right? This is the expression for, so I am writing this equation 1. So this is the expression for generalized displacement. For virtual work, for virtual work delta T equals to 0, right? Delta T equals to virtual time equals to 0, or del Ri del T equals to 0. Which one you can accept? So this is not acceptable to me. This is acceptable to me. Del Ri del T equals to 0 for virtual work, right? Or delta T, time is not involved, then delta T is also 0, right? So for virtual work, the equation will be this thing. So virtual displacement, this is displacement called generalized displacement. This is called generalized displacement, and the virtual displacement will be summation over I del Ri del Qi, sorry, del Qj, I'm sorry, del Qj delta Qj. I is there, so it will be summation over j, I guess. It will be summation over j, summation over j del Ri del Qj. Now you can remember this expression was written there for principle of virtual work. These Qj's are generalized coordinate, and this displacement is generalized displacement. Now what will be generalized velocity? Now if you differentiate this thing with respect to time, then number 2, we have seen that delta Ri equal to summation over j del Ri by del Qj delta Qj plus del Ri del T into delta T, right? Now velocity, generalized velocity Vi will be equals to Ri dot equals to delta Ri by delta T will be equals to summation over j del Ri del Qj into Qj dot, right, plus del Ri del T, where Qj dot equals to del Ri delta Qj by delta T, or T Ri del, I'm sorry, dQj Qj by dt equals to Qj dot. Differentiating with respect to time is called generalized velocities. So this is the velocity, this is the Vi equal to Ri dot actually. So this is the velocity, this is the expression for velocity, which can be written in terms of generalized velocities. Now if coordinate transmission does not involve time, then this term will vanish. In general this term will be there. So this Qj or this Qj is called generalized velocities. So at once you can find generalized momentum, but before that we have to consider generalized force, and then we will go to the generalized momentum or conjugate momentum. But I think today this much enough. I should stop here. In the next class, I'll discuss quickly about other generalized notions that is generalized force, generalized momentum, give some illustrate with few examples, and then finally we'll I'll derive Lagrange's equation from D'Alembert's principle. So thank you.